Ja, Magnus Nordgren heter jag alltså och jag tänkte berätta lite grann vad vi har hållit på och forskat på under snart ett år här. Det är ett axplock, eller rättare sagt mer en framtidsbild av vad vi ser i våran grupp som intressant område för massa- och pappersindustrin eller skogsindustrin i allmänhet. Och titeln är When Pulp and Paper Goes. Och vad goes den då? Plastic. Ja, det kanske är lite utmanande, men jag ska förklara lite mer vad jag menar med det här. Först och främst vill jag berätta att i våran grupp är vi idag 2 professorer, 2 gästprofessorer och 3 postdocs och 4 doktorander. Och hälften av de här människorna har börjat att arbeta inom det här området. Och vad menar jag med Pulp and paper goes plastic? Pulp and paper kommer alltid att finnas och papper kommer alltid att vara viktigt. Men jag tror, ungefär som Daniel nämnde idag tidigare på förmiddagen i det här two teams project, att vi kommer att se en utveckling där vi faktiskt, om vi applicerar det han berättade om lite längre fram i kedjan mot papperssidan eller massan istället för att ha det i processen, så kommer vi att kunna göra saker så att papper goes plastic. Tänk om man kan göra papper eller massa till ett designmaterial istället för, ja, man designar ju papper och förpackningar idag. Men tänk vad mycket mer man skulle kunna göra. Eller man skulle vilja göra. Det finns ju ganska många saker som är gjorda av plast. Och det är inte säkert att papper eller massa kan ersätta alla. Men jag tror faktiskt att vi kommer att se väldigt många mer produkter. Och det är en himmelsk flora av möjligheter om man börjar titta på det här. Va? Som inte bara är en tvådimensionell struktur, utan det är komposita material. Det är filmer, det är barriärer, det är inredningsdetaljer. Ja, plåster, hälsovård, sjukvård. Det är en väg framåt. Och på samma sätt, genom att utnyttja den här möjligheten att plastisera fiber och massa, vilket man kan göra genom att använda saker som gör att de molekylära interaktionerna mellan polymererna, till exempel i cellulosan, inte blir lika starka. Det är det som är nyckeln. Det är därför plast går att smälta. För att när man höjer temperaturen på en termoplast så kan man få rörelse mellan molekylkedjorna. Cellulosa däremot är en kristall till stor del med väldigt starka intermolekylära interaktioner. Det är de vi måste påverka för att komma hit. Och det är det vi kan göra. Till exempel med DES eller andra vattenbaserade faktiskt också lösningsmedel. Kan vi göra det, då kan vi göra mer saker som vi faktiskt gör lite grann idag också. Vi kan göra textiler. Och det vet vi ju redan att det finns massa används till exempel för viskosproduktion. Och viskos är ju ett tyg som vi har i skjortor och liknande. Vi kan göra enklare varianter också, agrotextiler. Det kan vi göra. Vissa av de här produkterna borde vi kunna göra i den befintliga produktionsapparaten som vi har idag i pappersindustrin. Så allt behöver inte vara nytt. Jeansen är svårt att göra i en pappersmaskin, men massan kan vi använda till något som vi kan göra i jeans av. Så att jag tycker egentligen det är inte så mörkt, utan om man tittar så ser jag verkligen en soluppgång i den norrländska taigan. Nu ska jag lämna över till Ran som får ta några mera konkreta exempel av vad vi håller på med.
Mm. Tack. Oui. Wrong button. So the title is not exactly on the paper. It's a more general discussion about the bio-based materials that I have been working with. And as Magnus told you, that my name is Ran. I'm a PhD student in Mid Sweden University. And before I started as a PhD student, I started did master programs in that place, and after I graduate, I start my adventures in the forest industry. And at the beginning, we are thinking about the bio-based materials. So we look at the market. We already have a lot of different kind of commercial product, like the bio-based film, bio-based plastic bag, bio-based hard plastic tableware, and also the beads from starch is quite common on the market recently. And we also have different kind of foamed materials from the bio-based materials. But if we look deep of those materials, we think it's not even they said the bio-based materials is not from the materials that we use from the wood, like trees directly. So what we want to use at the beginning is the materials that we recovered from paper mill, those extractives from the wastewater. We want to find some new application for those materials. So we look at the foamed materials because we think it's quite a variety of applications that we can use for the water absorptions, for the packaging materials, and also for the life saving, if you want to say it like that. So here is what we come. The materials we produced is in the middle. As you can see, it's quite sponge-like, and it's compressibles. It's also from the same pictures. It's quite porosity, and by changing the process. While making them, we can turn it into flexible materials or quite stiff materials. And also the density here from all the materials we produced is between 12 kilograms per cubic meter up to the 28 kilograms per cubic meters. We think it's pretty light materials. But as Tetsuo mentioned before, we have some materials, but what's the application that we can use it? We think it could be some water absorption applications. And here's a short video that I can show you. We have a small piece of our materials, and we squeeze it into a solid ball, and we drop it into the into water. And here is how it looks like. Oh, I should have from the beginning. Now it's the. You can see at around 4 seconds, it's back to the original volumes, and then it will keep absorbing water and the swellings, and up to the 11 seconds, it reached the maximal volumes. And here's some figures. I can explain it a little bit. The y-axis, the x-axis, is how much water the sample can absorb. It's measured as the total weight of the absorbed materials compared with its own dry weight. How much times. And the y-axis is the sample weight loss after 1 hour of absorption. We lose part of the materials in the solutions. And as you can see, most of the materials that we produced is at this range. It can absorb around 65 to 75 times of its own weight. But it loses 30%, 50% to 30% of its own volumes. So what kind of application that our materials can do? If you compare it with superabsorbent, it's not very impressive data, because the superabsorbent can absorb up to 400 times to 1,000 times of compare its own weight. But the good advantage of our material is that we have very quick absorption rate. As you can see from that these videos, it's only need 4 seconds to reach its volumes. And from some of our materials, it can be even quicker. It's under 1 second. It can absorb the probe liquid when we do the measurement as the dynamic contact angle measurement. So our materials can be a complement combination with superabsorbent. It can work as a buffering zones to absorb water at the initial stage and then slowly release it to the superabsorbent to let it lock the water. And the weight loss during the process can even turn to an advantage because it can release the space for the superabsorbent, so it won't take any space anymore. But we need some further research to check how much the dissolved materials can be locked in the superabsorbent. And while we're doing this kind of project, we use cellulose, silane, glutathione, glucomannan from the processed water, and those are quite sort of pre-treated materials. It's not original from the wood fibers. So we think, what can we do with the original fibers? That's why we come to the next project. It's the cellulose dissolution. Because there's a lot of solvent systems nowadays can efficiently dissolve cellulose or partly dissolve cellulose. The ionic liquid and also some other kind of solvent combinations like sodium hydroxide urea, lithium hydroxide and urea. And we choose sodium hydroxide and urea because it's sort of green chemicals. It's not hazard to the environment and it's relatively low cost. The process is also sort of mild conditions. We can control it. And our aim is not totally dissolution, since it needs a lot of effort to do that. So the partly dissolution is what we aim for. And what can we use the partly dissolved cellulose? We think we can use that to modify the paper surface. Because if we treat the paper surface, we dissolve the cellulose on the surface and we regenerate it, it can change the surface morphologies. So we have the starting materials as a liner board. And our idea for this project, because it's a relatively new project in our department, we think we can make some paper board, like a plasterized paper board, by dissolving the surface of one layer of liner board, and then we laminate different layer of treated materials. By regenerate the cellulose on the surface, we can adhesive them together, so one piece use its own materials. And furthermore, we can use those laminated board for paper suitcase or some other packaging materials like the wavings in the floating board. So we have the ideas and we have a few trials for those. At the beginning, we have this kind of process to produce laminated paper. We spray each piece of the liner board and then we laminated them together and washed out the exceed amount of sodium hydroxide and urea. We hot press it to regenerate the cellulose and then we achieve this kind of quite tough materials. But at these methods, there's a problem, it's not that easy to control to repeat the result because it's very hard to make sure we have exactly same amount of chemicals absorbed in the materials or we wash them at the same condition. So we came out this kind of methods. It's adapted from it's called the solution infusion process. It's adapted from the resin composite molding process, which use vacuum as the trapping, which use the vacuum to hold all the materials and suck in the solutions we're going to use and keep it in the composite and let it rest for a certain time. And here we have the vacuum trap at the outlet of the vacuums to recover the solutions. It can also cost the research. It can also reduce the cost of the research since we can reuse those amount of chemicals. And here you can see the laminated materials. We have a different layer. The base is the Arclay board to have a flat surface. And then we have a piece of polymer layers to prevent the material stick to the surface. And here is the paper that we are using. And we have another layer of polymers, compressors to keep some distance between the vacuum bag and the materials. We have this infusion mass to make sure that the solvent can go through the whole structures while the vacuum applied on the composite. And as you can see here, the dark area is where those soaked in the solutions, and those light area is haven't soaked in solution yet. So the solution slowly goes into the whole process. And here is the materials that we have after the process. And we use two simple methods to determine the result of our materials. One is the 2-point bending stiffness. It's have a clamp to hold the paper samples, and it start to turn at a certain angles. From the ISO, we use the 15 degrees measurement. And here is the force sensor to check how much bending resistant. And then after the calculation, we can turn to the bending stiffness. The second one is the short compress test. It's collapse the paper sample and push it towards each other at a very short gap to check how much force it needs to collapse the materials. And this is the data from the first methods, the spray, wash out, and hot press. As you can see, the reference is use water. The bending stiffness is 3 and 2 from the machine direction and the cross directions, and these are the treated materials. You can see most of those are double or triple the result. So we can provide some tough materials. And for this is the materials produced from the solvent infusion process. As you can see, the number is not that impressive. It's because even we have the vacuum to trap all the composites together. So it's not the adhesive process is not that well, so the paper is not really stick to each other. While the bending stiffness, the inner shear will delaminate the materials. So we have to work on that to make sure how can we achieve such a uniform materials. And for the short compression test, you can see the data is quite similar. So the 3-layer materials is around 23.4 kilonewton per meter. And here is also 22, 23. So the second one could be a good method, but we still need to work to refine the conditions and how to operate this process. And here is some partners working this project. And thanks for the financials and the help from the SCA. Yeah. And any questions?